If you are like me, there's no better way to spend a sunny Sunday morning than leafing through the back of the New York Times, doing all the little published puzzles. A personal favorite of mine, among Sudoku and crosswords, is the little decipher problem, a cryptogram, in which it is your job to construct a one-to-one mapping between letters that unscrambles the jumbled mess on the page. However, if you are even more like me, then you are rather lazy on Sunday mornings. As such, I set out to write an algorithm that would solve them for me. Taking inspiration from a paper by Diaconis, a mathematician from the University of Chicago, I present a Monte Carlo Markov chain approach to solving cryptograms. Let me begin with a very brief summary of Markov Chain Monte Carlo algorithms. MCMC, as will henceforth be called, can be summarized as follows. Let x be a finite state space and pi of x a probability on x. We define a positive matrix JXY on x initially unrelated to pi. The algorithm slightly modulates J to a new matrix K. We accept K based on some acceptance ratio. If the correlation of K is greater than that of J, we choose K always. If not, we choose K with probability T times K over J, where T is some normalizing constant. In this sense, the selection of K is almost greedy, except for the possibility that we choose a less probable K with some non-zero probability. The manifestation of this method in our problem will be outlined below. As mentioned earlier, cryptograms are based on one-to-one alphanumeric mappings. For simplicity's sake, I will only consider such mappings between uppercase letters of the English alphabet, i.e. a function f that goes from alpha to alpha, but this technique is easily generalized to other sets of symbols, assuming they can be read by a computer. In order to calculate the validity of any chosen map, we must first establish a criterion by which to judge it. This is accomplished by a frequency analysis of some reference text. This analysis is relatively simple. Loop through each character of the reference text, counting the number of times every other character follows the one in question, i.e., count how many times does D follow A. From this, we create a matrix where each row and column corresponds to either a letter of the alphabet or any other special character, space, period, comma, etc. We treat them all the same. In this container, each cell holds the number of times character X is followed by character Y. Dividing by the total number of occurrences of each letter in the text, we establish a transition matrix, a matrix of probabilities for any character to follow another. For this project, taking cue from Diaconis, I used Tolstoy's War and Peace due to its great length. We see, as demonstrated in the figure, our calculated probabilities make qualitative sense. The letter Q is almost invariably followed by U, D and Y are most likely to end words, followed by periods, spaces, commas, etc., and common patterns like T goes to H, V goes to E, and J goes to U are very prevalent. From the transition matrix, it is possible to calculate the likelihood a general map correctly predicts the decoding pattern. We accomplish this by defining the plausibility of F to be the product of the probability F of S is followed by F of S plus 1, where S is taken over all characters of the encrypted text. In other words, we simply compare the likelihood that character patterns predicted by F match those discerned from our reference text. For example, if F takes a pair SO and maps this to HE, we would consider it rather likely. However, if F maps SO to XB, we would surely throw it out. Once we've established a method for characterizing each map, it is time to devise an algorithm for predicting the best map possible. We proceed to follow the standard MCMC method as outlined. Begin with the encrypted text, then guess a random mapping F. Compute the plausibility of F as previously defined. Randomly switch two map variables to obtain a new map, F star. Compute the plausibility of F star. If the plausibility of F star is greater than that of F, keep F star always. If not, keep F star with plausibility of F star over plausibility of F. We let this run over many hundreds of iterations. In our case, the general set X is a set of all possible mappings. The matrices J and K are the probability matrices defined by applying F and F star, and pi of X is the plausibility function. Throughout this process, our job is to pick random mappings F from the probability distribution pi of F. Despite the immense size of F space, the Markov chain application solves the problem. Although MCMC is technically greedy and thus prone to becoming stuck on local minima, the stipulation that we are allowed to pick a less likely mapping with some probability ensures that we will eventually find the correct solution, given we are patient. By the usual Markov chain convergence theorem, after many iterations, the algorithm is likely to be at a decryption key, which gives decryption text pair frequencies close to those of the reference text, and is thus more likely to be correct. That is, the algorithm produces plausibility functions which converge in the limit to the maximum possible value. In essence, the repeated application of a standard distribution to our matrix will see the result converge to an eigenvalue solution in time. Before we try and solve any actual puzzles, let us first see if we can decrypt some known text. Consider Hamlet's soliloquy in its entirety. If we randomly scramble the characters due to some random substitution cipher, as shown, can our algorithm discover the inverse map? We see that initially, after around 10 iterations, the proposed map effectively returns gibberish. However, after many more iterations, a few hundred, we see that the map has essentially converged to the desired solution. This is quite encouraging for the overall problem. However, what happens when we try and solve an actual cryptogram, a problem of substantially shorter length? Unfortunately, we find that as the length of our desired text shrinks, our algorithm decreases in accuracy. For example, consider this much shorter problem. After the same number of iterations required for convergence in the Hamlet case, we see the algorithm has not converged to much of anything. In fact, even after 10,000 iterations, the story is much the same. Frankly, we should expect this to be the case. The method is predicated on numerous points from which we compute the plausibility of f. Diaconis and his colleagues remarked that the ciphertext should contain at least 2,000 characters. Clearly, any regular cryptogram is much shorter than this. The provided example corresponds to a measly 250 characters. The algorithm must be provided with sufficient space to move around, and the minute size of regular cryptogram problems is simply too small. Now, what does this ultimately entail for me on Sunday mornings? If, on one hand, I am faced with many distinct cryptograms of long sum total length, I can certainly use my program to decrypt all of them at once, which is quite handy. On the other, more unfortunate hand, the prospects of solving a singular problem do not look so great. Regardless, the methodology remains successful. Clearly, MCMC is a viable technique to search for solutions to ciphers on any day.